In this lesson, we're going to take a look at intramolecular forces. So we'll look at ionic bonds, polar covalent bonds, and nonpolar covalent bonds. So the different types of molecular forces, we have two major categories. Intramolecular, which are the bonds within a molecule, and that's what we're going to look at in this lesson. And in a subsequent lesson, we'll take a look at intermolecular forces, so the forces between separate molecules that pull them together. So intramolecular forces, similar to intramural sports, that involves competition within the school. So an intramolecular bond, we're talking about the forces within a molecule, so between the different atoms that are in a molecule. So if I take a look at water here, the bond between oxygen and hydrogen, those are the intramolecular bonds, so the bonds within the molecule of water. With sodium chloride, the bond between the sodium and the chlorine here is also an intramolecular bond. So in the previous one with water, water was a covalent bond because oxygen and hydrogen are both non-metals, and sodium and chlorine we have a metal and a non-metal. So this is an ionic bond. But the bond between those two atoms within the molecule of sodium chloride is what makes this also an intramolecular. So both of these we're talking about intramolecular. Okay, so polar and nonpolar in that starting slide, that is probably something that is new to you. So far, we have just talked about ionic bonds being the gain or loss of electrons, which creates positively charged ions or cations and negatively charged ions or anions, and then the force between the positive and negatively charged ions then holds those two ions together in a bond. So that's an ionic bond. And we've talked about covalent bonds as a sharing of electrons. But sharing of electrons is not always equal. So if the electrons being shared is completely equally shared between the two atoms, then we have what we call a nonpolar covalent bond. If, however, one of the atoms is pulling the electrons a little bit closer to itself, so there's not a full transfer of electrons like in an ionic bond, but one atom may have a stronger pull on electrons, so it may pull it a little bit closer to itself, and that creates an unequal sharing of electrons and what we would call a partial positive and partial negative charge. So it's not a full movement of electrons, just electrons are a little bit closer to one atom, which makes that area slightly negatively charged, and electrons are moved a little bit further away from the other atom, which makes it slightly positively charged. So this symbol you see here is a Greek symbol, and what that means is slight charge. So this is a slight positive charge, and that's a slight negative charge. Whereas with ionic, we get a full positive and negative charge. So how do we figure out the polarity of atoms? It is based on electronegativity. So we've talked about this when we looked at periodic trends. So electronegativity is just the ability of an atom to attract bonding electrons to itself. So what does that mean? Bonding electrons are the valence electrons that are going to be involved in the bonds. So not even all valence electrons, just the ones that will be involved in the bond. So if I look at hydrogen, hydrogen has 1 electron, oxygen has 6, and the other hydrogen has 1 as well. So we're going to have a sharing of those electrons and a sharing of those electrons. And so in this case, hydrogen's 1 electron are bonding electrons. And for oxygen, this electron and this electron, which are involved in the bonds, those are the bonding electrons for oxygen. So electronegativity is the ability for hydrogen and for oxygen in this case, to actually pull one electron towards itself. So for oxygen, the ability to pull this hydrogen electron towards itself and its own electrons, so these bonding electrons towards itself. And then for hydrogen, it would be the ability to pull the bonding electrons there. So this has to do with a strength. Which one is more electronegative? Which one is better at pulling electrons to itself? This is based on in relation to one another. So this is an assigned scale. It's not an actual measured value, and it's just based on in relation to one another how well each atom can pull the electrons to itself. That has to do with the trends that we looked at in a previous lesson. So atomic radius, how far away those valence or bonding electrons would be from the positively charged nucleus, and the ionization energy, so the amount of energy that is released when an electron leaves that atom. So in a periodic table, I've added this in your OneNote. The electronegativity on here, so electronegativity scale was not on the other periodic tables you have, so I've added this in. So when I look at an element, the number right above the symbol is the electronegativity. So they're assigned in relation to one another. So fluorine here has the largest number at 4. So as we look at all the other numbers, none of them are going to be this high. And francium has the lowest number at 0.7. So that means out of all the elements in the periodic table, fluorine is the best at pulling electrons towards itself. And if I look at fluorine, fluorine has 7 valence electrons, so it only needs to pull one in. And then the other thing is fluorine is in the second row, which means that there are only 2 rows or 2 shells of electrons for fluorine. So that means that the valence electrons are very close to the nucleus and that positive pull from the nucleus. So it is going to be very good at pulling an extra electron from somewhere else in to fill its shell, because that electromagnetic pull from the nucleus is so close to where those bonding electrons would be, and it only needs one more. So as I move down, all of the other halogens also only need to pull one more electron in, but as we add subsequent shells of electrons, the pull from the nucleus is further away from the electrons, the valence electrons, and so the electronegativity becomes less. It's not as good at pulling it in. Francium, on the other hand, has only 1 valence electron, and so it is not going to be good at pulling electrons in, because it would need to pull 7 in, which is a lot. So pulling 1 electron in is not easy for it, and it has many layers of electrons before we get to the valence, and so the pull to that outside shell is very low, because we have a lot of shielding from all of these full shells of electrons before we get to the valence shell. So there's a lot of shielding from the charge in the nucleus by the time we get out to the valence electrons. So this just says a lot of what I just did, that fluorine has the greatest electronegativity at 4 because it has the greatest ability to attract in an electron, and francium has the lowest at 0.7 because it has the lowest ability to attract a bonding electron to itself. So in general, the electronegativity increases as we go from left to right. So as we have more full valence shells and we have less electrons that need to get pulled in, and it also decreases as you move down a group and add more shells of electrons, because we have more what we call shielding, which just means that the distance of our valence electrons is further away from the nucleus, which is what is pulling the electrons in. So what we do to figure out the the difference in electronegativity to determine whether a bond is ionic or covalent. We will take the electronegativity for the two atoms involved in any bond and calculate the difference between them. So whichever one is more electronegative, the electrons are going to move closer to that. But the actual value, so how different those electronegativities are, will determine if there's a huge difference and something is very easily going to pull electrons over and fully pull them over and result in an ionic bond, if they are completely equally shared, so if there's no difference between them, or if we're somewhere in between. So the numbers we're looking for are 1.7. If the difference in electronegativities is bigger than 1.7, then that bond is going to be ionic. If it's less than 0.5, then it's going to be a non-polar covalent. And if it is between 0.5 and 1.7, then it's going to be a polar covalent. So there will be a shifting of the electrons closer to 1, not quite enough to fully have that electron move from the valence of the one atom to the other atom to create ions, but enough that we have a slight positive and slight negative charge created. So a polar bond is one that has a slightly positive charge at one end and a slightly negative at the other. So remember that that symbol, that Greek letter, stands for slightly. And that's based on the difference in electronegativity from one atom, the one with a greater electronegativity, pulling the electron a bit closer to itself, creating that slightly negative charge. And a non-polar bond, so that one is where the electrons are shared equally. So the completely equally would be when we have, for example, diatomic. So from our Hofbrinkel, if we look at hydrogen, two hydrogens, same atom, same electronegativity, so will result in a delta En, or a difference in electronegativities of 0. And so those electrons are shared completely equally. Ones that are off by 0.1, 0.2, 0.3, 0.5, those are also going to be shared fairly equally, and so those will be a non-polar bond. So if we look at some examples here, carbon and hydrogen, so I'm just looking on another copy of that periodic table. So carbon is 2.6 and hydrogen is 2.2. So my change in electronegativities is equal to 2.6 minus 2.2, which is equal to 0.4. So that is a non-polar covalent bond. Hydrogen and nitrogen, so nitrogen is 3.0. And we just saw hydrogen is 2.2. So when I do that subtraction, I end up with 0.8. And so that is a little bit above 0.5. So that one is a polar covalent bond. Magnesium and chlorine. So magnesium is 1.3 and chlorine is 3.2. So my delta En here is 3.2 subtract 1.3, which, if I'm correct, is 1.9. That's over 1.7, so that's going to be ionic. And calcium and fluorine, so fluorine was 4.0, and calcium is 1.0. And 4 subtract 1, so my delta En is equal to 3, which is also ionic. Okay, so using that periodic table, we can calculate electronegativities to see in relation to one another two different atoms. Is one going to be strong enough to completely pull electrons over to make a bond ionic? Is it going to pull them over somewhat closer to 1, making a slightly positive and slightly negative area, making that bond polar? Or are the electrons going to be shared equally or almost equally, making it a non-polar covalent bond?